Within the standard calculus curriculum, most classes will introduce you to seemingly a battery of tests that seem, well, different, a little bit out of place maybe. Things like the geometric series, p-series, harmonic series, telescoping series, alternating series, integral test, root test, ratio test, comparison test, limit comparison test, and some classes will even go past this. And you may ask, why? Why here? Why now? What's the purpose? Hello, welcome back to the Quant Plus YouTube channel. To answer the question posed at the beginning, I can't give a fully satisfactory answer. But what I will say is that sequences and series are an important part of mathematics in general, although it seems a little bit out of place, right? Things like the integral test or the limit comparison test, and really a few of these tests directly relate to the standard calculus curriculum in terms of concepts such as improper integrals and limits and things of that nature. And another reason is that you can leverage these concepts with power series and with other approximation techniques that let you approximate and re-express functions in terms of polynomials, which, as I hope you'll see by this point, polynomials are generally speaking a lot easier to work with than, say, your trigonometric functions or logarithmic functions or things of that nature. As we alluded to, power series, well, one, they directly relate to functions, right? They allow you to express a whole range of functions really as polynomials, or really infinite sums, aka infinite series of polynomials. With one quite common example, you can express the function 1 over 1 minus x as the series from n equals 0 to infinity of x to the n. And if you see the similarities to the general form of the geometric series sum, yes, you are correct. So when you're working with power series, much like maybe previous concepts in terms of all these limit tests and sequences and series as a unit within the standard calculus curriculum, you have this idea of the interval of convergence. And pretty much the idea is for what x values, right, for what domain of values will the series that you wrote out converge. And so we have a standard way of doing that related to your ratio test. And if you think about the inside of your series, which I'm going to write as an times x minus c to the n, where what I forgot to mention earlier is that c is the center of your approximation. Much like if you think back to a previous class in terms of graphing, if you have the function y equals x squared, you know that that's a parabola that opens upwards and has a center at x equals 0. Whereas if you have y equals, say, x minus 5 quantity squared, then you still have a parabola that opens upward, but that's the center of that new parabola is going to be at x equals 5. So in a very similar way, you want to know around which x value you're centering your power series, right, or your approximation, and that's what that c does for you. Now, jumping back to what we're talking about, if we express this as this sequence inside of our series, an times x minus c to the power of n, in terms of some temporary variable, which I'll label un, then we can apply the ratio test. And in the context of power series, if you have the limit as n approaches infinity of the absolute value of u of n plus 1 over un, and this is less than or equal to 1, then you have absolute convergence. And this doesn't necessarily address the borders, right, or like the cutoffs of the interval, but you can individually plug in those values and see the convergence or lack thereof at those particular points. So jumping back to our previous example, if we consider the function f of x equals 1 over 1 minus x, as we saw before, we are provided that we can express this in terms of the sum from n equals 0 to infinity of x to the n. Well, if we consider the sequence inside of our series, we have the sequence which I'll label as u sub n is x to the n. And if we consider the limit as n approaches infinity of u n plus 1 over un, we'll get the limit as n approaches infinity of the absolute value of x to the n plus 1 over x to the n. And this becomes the limit as n approaches infinity of the absolute value of x, which is simply the absolute value of x. And if we consider that this has to be less than 1, then we get to the interval -1 to 1. And we know that in that restricted interval, we're going to have absolute convergence. Now, as for the values at the border, we can directly plug those in. So if x equals -1, right, then our sum becomes the sum from n equals 0 to infinity of -1 to the n, and we know that that will diverge, right, because you're going to get +1 for even multiples or even values of n, and -1 for negative values, and it's going to just jump back and forth, back and forth, back and forth, never coming to rest at any particular point. If we plug in x equals 1, we can also see that we're going to get a diverging series because we're going to get the sum from n equals 0 to infinity of 1, and this is going to be infinity, so that will also diverge. And so what that means is that in our particular case, we have an interval of convergence from -1 to 1, and that means that if we restrict our x values to be in that range -1 to 1, not including our bounds, then this sum will converge, and you'll see in the future that this actually converges to 1 over 1 minus x in that interval. Now, the next concept I want to remind you of, or you may have seen this, or this may be the first time you're seeing this, are Taylor polynomials. So in general, Taylor polynomials take the form f of c, meaning evaluate the given function that you want to approximate at c, then consider the first derivative evaluated at c times x minus c, plus the second derivative evaluated at c over 2 factorial times x minus c quantity squared, and so on up until the nth derivative evaluated at c over n factorial times x minus c to the n, where the specific value of n will change question to question, problem to problem. So as an example, if we consider f of x is sine x, we can take the derivatives, right? So if we have f of x equals sine x Then we have f prime x, the first derivative is cosine of x. The second derivative is negative sine x. The third derivative is negative cosine of x. And the fourth derivative gets us back to sine of x, and this pattern will continue. And then because in this particular example we're centered at x equals 0 or c equals 0, we're going to evaluate each of those expressions at 0. So f of 0 is sine of 0, and that's 0. F prime of 0 is going to be cosine of 0, and that's going to be 1. F double prime of 0 is going to be negative sine of 0, that's again going to be 0. Third derivative, evaluated at 0, is going to be negative cosine of 0, that's negative 1. And finally, the fourth derivative, evaluated at 0, is going to be sine of 0, and we saw that is again 0. Combining this with the fact that because c equals 0, we're going to get x, x squared, x cubed, and so on, we can approximate the behavior of the function sine of x near x equals 0 by the polynomial x minus x cubed over 3 factorial plus x to the fifth over 5 factorial. A related concept is Taylor's theorem, and Taylor's theorem says that you can consider whatever function that you want to consider f of x as some approximation up until degree n, right, according to this general form of Taylor polynomials, which, let me scroll up 1 second, is right here, plus some remainder term. And according to Taylor's theorem, this remainder term is defined as the n plus 1th derivative evaluated at some point z, where that point z is somewhere in the interval of values that you're considering, over n plus 1 factorial times x minus c to the n plus 1. And one very useful consequence is that the absolute value of your remainder term, which is labeled the error term, which is defined as the absolute value of of the n plus 1th derivative evaluated at z over n plus 1 factorial times x minus c to the power of n plus 1, is less than or equal to the maximum value of the n plus 1th derivative evaluated at c over n plus 1 factorial times x minus c to the n plus 1. And so in maybe more everyday language, what this is saying is that there is a maximum difference, right, between what the function's value actually is and our approximation. And if we add additional terms to our approximation, the polynomial that we're using to approximate the function, we're going to get a better and better result. But still, even if we have a rather simple limited approximation, we're going to get fairly decent approximations in many cases. So let's look at a particular example. So approximate sine of 0.1. Referring to what we were talking about in our previous example, we said that sine of x can be approximated by the polynomial x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial minus, and this keeps going on, right? Well, at least if your values of x are fairly close to 0. If we approximate sine of 0.1 by saying 0.1 minus 0.1 cubed over 3 factorial, we'll get 0.1 minus 0.001 over 6. Plugging that into a calculator, what we'll get is approximately 0.1001. And, well, how good of an approximation do we have? Well, by the definition, the absolute value of your remainder term, which is defined as the absolute value of the n plus 1th derivative evaluated at z over n plus 1 factorial times x minus c to the n plus 1 is bounded above, right, by the maximum value of the n plus 1th derivative over n plus 1, right? You consider the maximum of this expression right here, or of that term right there. Well, because we're dealing with our sine function, we know that the n plus 1th derivative of sine of x is going to be either plus or minus sine of x or plus or minus cosine of x for every possible n, right? Because we know that it comes in cycles of 4, so you'll get the original function is sine, then the derivative is cosine, then negative sine, negative cosine, and back to sine. And we also know that sine and cosine, at least on the real numbers, that both cosine of x and sine of x are both less than or equal to 1 for every possible real number. And what that allows us to say is that in our particular case, we know that our approximation is going to be less than or equal to the absolute value of x minus c to the n plus 1 over n plus 1 factorial. Well, let's plug in some values. If our approximation is centered at x equals 0, and we're considering x equals 0.1, that means that our range of values happens between, the range of values that we're considering is x is between 0 and 0.1. And so that means that our error term, which is going to be less than or equal to the absolute value of 0.1 to the next term in our sequence, which, if we're considering the first two terms up until x cubed, technically there is the fourth term in your approximation, but the fourth quote-unquote term is going to 0, so we're going to consider the next term in our polynomial. That's going to be x to the 5th over 5 factorial. So accordingly, we're going to say 0.1 to the 5th power over 5 factorial as the largest possible error bound, meaning the largest possible difference between our approximation and the true value of sine of 0.1. And in doing that, this rounds to 8.33 times 10 to the negative 8. So what that's telling you is we have a pretty good approximation with a very, very simple polynomial, right? We only considered the first two terms, x minus x cubed over 3 factorial. Now, combining the two concepts that we were referring to, we have Taylor polynomials, right, which are up until some degree n, whatever that n is in your particular application. And we have power series that are infinite series, right, infinite sums of polynomials that allow you to re-express common functions. So a Taylor series is of the form the sum from n equals 0 to infinity of the nth derivative evaluated at c, where c is the point of interest, over n factorial times x minus c quantity to the n. And there are some very useful properties. I'm including them with the Taylor series, but these are actually properties of power series, and Taylor series are power series, so they're kind of interchangeable ideas there. The first property is that if you have some power of, if you're evaluating f at some power of x, let's just say x squared, x cubed, or so on, you can evaluate your polynomial, let's just say your polynomial centered at x equals 0, and just directly plug in that new power of x. Instead of x, you might have x to the n. If you have a constant k multiplying your x, then you can again evaluate your expression, and the way that that's going to affect your sum is that you now have k to the power of n in your sum for each term. And the last common property that I'm going to include here is that if you consider the sum or difference of two functions, then you can express their power series as the sum or difference of their sequences times x to the n. So let's jump to a particular example. The one I'll be referring to here is e to the x. And what we know is that the nth derivative of x, the nth derivative in terms of x, right, in terms of a function is e to the x, regardless of what n is going to be. It's one of those unique and helpful properties of e to the x. And if we are centering our approximation at x equals 0, we know that e to the x evaluated at 0, so e to the 0 is 1, always. That means that we can actually express our function e to the x as the sum from n equals 0 to infinity of x to the n over n factorial, like that. Here I wanted to give you one more fairly common example, or maybe not a fairly common example, but a useful application of these concepts. And what I failed to mention earlier is that when you integrate or differentiate a power series, you integrate and differentiate the individual terms. And we'll see that play out in 1 second. If you recognize this as being the probability mass function of a standard normal distribution, i.e. one with a mean of 0 and standard deviation of 1, great. But let's still leverage these concepts to get a fairly decent approximation of things. Now, referring to our previous example, we said that e to the x can be expressed as the sum from n equals 0 to infinity of x to the n over n factorial. And referring to the property where you can evaluate this series at some power of x, we can re-express e to the negative x squared over 2, like this, as the sum from n equals 0 to infinity of negative x squared over 2 to the n over n factorial. And simplifying this, we end up re-expressing this as negative 1 to the n times x to the 2n over 2 to the n times n factorial. Okay. From here, we can integrate this. So we can say that the integral of e to the negative x squared over 2 dx is the integral of this sum dx. Now, yes, I am expressing this without bounds, so technically this is an indefinite integral and you do need the plus c, but I'm going to skip that for now because in our application we are going to consider bounds. So, what I was referring to earlier is that we can still write this as the sum from n equals 0 to infinity, and we're going to integrate each of the individual terms, so we still have a negative 1 to the n, but the integral of x to the 2n is x to the 2n plus 1 over 2n plus 1. And that means that our new sum is x to the 2n plus 1 over 2n plus 1 factorial. Sorry, not factorial, sorry, just 2n plus 1 times 2 to the n times n factorial like this. And if we plug in values, so we integrate from, let's just say, 0 to 1 as it is in our problem, this can be thought of as evaluating this sum at 0 and at x equals 0 and x equals 1. Now, what's nice is that if we evaluate this at 0, x equals 0, you're going to get 0 to the power of 2n plus 1, which is always 0, so you really only have to worry about plugging in 1, and that means that we can re-express this as the sum from n equals 0 to infinity of negative 1 to the n over 2n plus 1 times 2 to the n times n factorial like that. Finally, to account for that constant of 1 over the square root of 2 pi in the given formula, or the given expression, we're going to say that one over the square root of 2 pi times the integral from 0 to 1 of e to the negative x squared over 2 dx is 1 over 2 pi, the sum from n equals 0 to infinity of negative 1 to the n times 2n plus 1 times 2 to the n times n factorial. And plugging this into a calculator, sorry, there should be a square root here. Plugging this into a calculator, we get an approximate value of 0.3413. And if you're familiar with the empirical rule in statistics, it says that between 1 standard deviation below the mean and 1 standard deviation above the mean in a standard normal distribution, you should have approximately 68% of your data, meaning that between the middle of your standard normal distribution, which corresponds to a z-value of 0, and as z-value of 1, meaning 1 standard deviation above the mean, you should have approximately 34% of your data. Our approximation says it's 0.3413 or 34.13%. To summarize the context of this video, while the sequences and series unit within the standard calculus curriculum appears out of place, it leverages standard calculus concepts such as integration, limits, occasionally L'Hopital's rule, and other techniques that are introduced within the standard curriculum. And one really important application of this is in terms of power series and Taylor series and Maclaurin series. Maclaurin series are a special case of Taylor series, which I didn't explicitly mention, but they are Taylor series centered at x equals 0. And while sequences and series by themselves are an important part of mathematics, one really useful application of them is in terms of numerical approximation. As we saw in our example, we were able to approximate the value of quite a complex integral by leveraging these techniques. Thank you for the support thus far on the channel, and I would appreciate if you would like this video, share it with your friends and family, and subscribe to the channel. And lastly, if you're interested in one-on-one tutoring sessions, please follow the link in the description below. Have a great day.